let's start today's session. We have oh my just so we'll have a geotech session today. Three simple questions. We'll discuss three questions. First is going to be related to foundation engineering. Second is soil mechanics, and third also soil mechanics, classification of soil. So let's start our session. The first question, okay, 2011, question number 13. Two geometrically identical isolated footing X and Y are shown in this figure and they have identical loading. Now the soil reaction will be A, uniformly distributed in Y but not in X, B, uniformly distributed for X but not for Y, C, uniformly distributed for both X and Y, and D, not uniformly distributed for either of them. So when we are solving this question, we have to remember few things. First, what do we say when what do we mean when we say something is rigid and something is flexible or linearly elastic in this case? So when we say rigid, so this is a footing, we are calling it rigid. That means there is not going to be any this kind of deformation, right? And if it is rigidly attached to a column of a particular, you can say, uh, building, then it is also not going to do like this, because this joint is also rigid. This 90-degree also will be maintained. So when we have such a rigid footing and we are talking about settling, then we have to assume that this whole footing is going to come down with the same rate. So they will be, so when there is a when the rate of movement of all these points is same, that means there is going to be uniform settlement. In case of rigid, in case of uh, flexible, it is allowed to move like this based on the pressure. It is allowed to do some other fancy kind of behavior. All right. So in case of this flexible footing, it is allowed to move to adjust the pressure. So finally, what ends up happening in flexible footing is that the uh, so the excuse me, someone's asking to move. So yeah, so as I'm saying, when we have flexible footing, what ends up happening is the footing deforms itself in such a way that the pressure at each point in the footing is the same. The pressure applied by the soil at each point in the footing is the same. So, like it's if we have if we have clay soil, it will bend something like this, and then the pressure will be same, but the settlement is going to be different. So, uniform pressure, but settlement not uniform, right? So here we have uniform settlement, but pressure not uniform. So what we end up what we have all the scenarios which we talk about, the combination of linearly elastic footing and then rigid footing with clay soil or cohesive soil and non-cohesive soil, we will end up with four combinations. And just for the completeness, let me also mention all these combinations and what is the distribution of the pressure and of the uh, settlement profile in these cases. So let's see. Let's say we have here on the next page. Let's see. We have here rigid footing, and we have flexible, and here we have cohesive soil, and here we have non-cohesive soil. So the answer to this question, actually, this particular question, uh, will end as soon as you know that in case of rigid footing you have uniform settlement, and in case of flexible footing you have uh, uniform contact pressure. But just for completeness, I am going to write all these scenarios. So when you have rigid footing and you have cohesive soil, then your settlement is uniform, but your contact pressure is actually minimum at the center and maximum at the edges. Okay. When we have flexible footing, then again uh, your contact pressure, maybe I will draw it, that is going to be more complete. So your settlement is uniform, right, and your contact pressure is maximum at the edges and minimum at the center. Now when you have flexible footing, in case of cohesive soil, what will you get? You will get the uniform pressure or the contact pressure, and your settlement is going to be non-uniform. It will be maximum at the edges, sorry, maximum at the center and minimum at the edges. Now let's go to the rigid footing with non-cohesive. So let me just write here, this is settlement, and this is contact pressure. Okay. So when you have rigid footing in cohesionless soil, like sand, your settlement is going to be still uniform, but your contact pressure is going to be maximum at the center and minimum at the edges. So in some of the drawings, I see that they have made it 0 at the edges. So we are also going to keep it like that. Uh, Now, when we have flexible footing, what will we have uniform? We have uniform contact pressure, and settlement is going to be non-uniform, which is going to be maximum at the edges and minimum at the center. This is something that you can either take a screenshot of, or you can, memorize this. Now, take a note of this. But now I want you guys to tell me the answer to this question. So the question is that you have two footings. X is linearly elastic, Y is rigid. Which one is going to have uniform contact pressure, and which one is not going to have uniform contact pressure? You can put answer in the chat box. A is the correct answer. So you're saying it will be uniform for Y but not for X. Correct. So A is the correct answer. With this, let's go to the next question. This question is related to SPT, Standard Penetration Test. The question is 2019, GATE 2019, question number 11. Dilatancy correction is required when a strata is A, cohesive and saturated, and also has N value greater than 15, saturated silt fine sand, N value less than 10 after overburden correction, saturated silt fine sand after overburden. Very good, correct answer. So saturated silt fine sand and value greater than 50 after overburden correction. Coarse sand under dry condition and N value less than 10 after overburden correction. Now in SPT, how many type of corrections we have? We have two type of corrections. One is overburden, sorry, and second is dilate density. So when we have a granular soil, in that case, what happens? Its value. Basically, let's start with SPT itself. What is SPT? So SPT, standard penetration test. We do this test to explore the vertical variation of different kind of soils that we have in particular area. So we let's say that this is our ground. We dig a small hole. We dig a hole here, and then we put uh, two split auger. So basically, the cross section looks like this. So this is the point which faces down, and these are the sharp edges that kind of penetrate the soil, and your sample of soil gets stored in this place. Now, but then you can use this sample to do different kind of tests, such as liquid limit tests and other kind of tests to identify whether the soil is clay soil, and what is the water content and all this. So what we do is we place this particular auger, not auger, we place this sampler on this soil, and we have a shaft on top of it where we drop a hammer. I'm just going in rough terms, and then I'll specify what are the details of the drop height and all those things. So we drop a hammer here, and this, as a result of that, this particular sampler goes into the soil, and then we measure how many number of blows of this particular hammer it took for this soil to go uh, down, for this sampler to go down by 15 centimeters. So we do it three times. So first time 15 centimeters, how many number of blows it took? We note that value. Then second time 15 centimeters, how many number of blows it took? We note that value again. Third time again 15 centimeter at the same location, it goes down, and how many number of blows it took? We take that value also. We record the first 15 centimeter for the number. Okay, thank you guys for waiting. I don't know, it's frustrating. This internet, it's not when we are not at the place. Yeah, okay, let's leave that. So, yeah, so where was I? I was saying that we have recorded the number of blows for three 15 centimeter intervals, but we ignore the first number of blows for the 15 centimeter interval, saying that it is a setting value. So we want the sample to nicely sampler to nicely settle in this particular soil, and we don't want any left or right distribution or alignment in that. So we say that first to 15 centimeter is just to set this sampler into the soil. So we ignore that, and only the last 30 centimeters, or it is also said 300 mm if you want to go in that convention, that value of the number of blows is used for the test. Now coming to the specification, what is the weight of the hammer? It is 63.5 kg. What is the drop height? So how many centimeters do we lift it up and drop it? We lift it up by 76 centimeters, or somewhere it is written as 75 centimeters. And what is the frequency of this dropping? So we definitely we need to follow some rhythm, right? So we need to drop it in some certain number of times in a minute. Otherwise, if you drop it very slowly with a very low frequency, Then after, let's say, one drop, you allow the soil to settle. And you might be familiar with that, when you shear a soil, after some times it kind of regains its shear strength. So we have to follow, as much as we can, we have to follow a constant kind of frequency, and that is 100 drops per minute, right? So that is the frequency we follow. All right, now let's come to the correction. Now that you have done this test and you have the value of n for these two 15 centimeter intervals. So for the last 30 centimeter, you have them. The thing is, in case of granular soil, this n is related to your relative density. Now, when a soil is having higher relative density, that means it is more nicely packed together. And in that case, you will need more number of blows to penetrate the same depth. Whereas for the granular soil with less relative density, you will need less number of uh, blows to penetrate the same depth. But what happens, it's not only this relative density that kind of impacts this uh, trend in the number of blows. The thing is, if you have a soil at higher depth, let's say you have a very high depth here, this particular soil sample where your sampler is penetrating is also subjected to the side pressures from the soil, that is the lateral pressure, or you can say even confining pressure. The more the confining pressure, the difficult it is the auger to move down, because when the auger moves down, it displaces the soil little bit on the right and left side. So the more depth this particular the more the depth of the soil, the difficult it is for the auger to displace it, and thereby more number of blows is required. So now uh, this particular difference in the confining pressure sometimes makes you overestimate the hardness of this the relative density of the soil, right? That's why we do this overburden correction. We do this overburden correction for granular soil to account for the confining pressure. Okay. Now, what is the formula for this overburden correction? If no, maybe, yeah, let's look at the formula for this overburden correction. Why not? So we have n dash is equal to n 350 divided by s plus 70, and this s is nothing but the overburden pressure less than 80 kilonewton per meter square. So this is the formula for your overburden pressure. N is for the 30 centimeter depth, the raw value that you got from the SPT test. Now, when you have done this overburden correction, this new value you got, this is the N dash. You are going to do the next correction, that is the dilatancy correction on this value. So you will get another value n double dash while doing the correction on this value. So you will have n double dash is equal to 15 plus 0.5 into n dash minus 50. That means right here dilatancy correction. Now when do we do this correction? We do this correction when your n dash. So Bridge already wrote in the chat. We do this correction when you have n dash greater than 15. When your SPT test value is greater than 15 after you have done your overburden correction. If it is less than 15, just leave the n double dash also as that particular value. And if it is somehow, let's say it is something, some value which makes the correction, uh, yeah, so basically if it is less than 15, and then you just leave, don't apply the dilatancy correction. Now, when do we apply this dilatancy correction? So when you have filthy sand or fine sand below the groundwater table, when they are saturated, and you have them below the groundwater table when they are saturated, then we know what happens, right? We know then, from Tarzagi's cell experiment, that when you apply a sudden load on that top of the saturated sand or saturated fine sand, there is a development of negative pore water pressure. So immediately that particular pressure that you have applied does not go to the soil. It is taken up by water, right? It is taken up by water instead of the soil, and only after time passes that particular water is going to drain out, and you will have the load transfer to the soil. So because of that development of the negative pore pressure due to the dilatancy of this saturated fine sand, we are going to apply this correction, because we will end up otherwise overestimating the strength of the soil. All right. I'm really sorry, guys. This January month is not it's not been good for me. I have to travel a lot, and these kind of issues we are facing. Yeah. So what I was saying. So we have seen from Tarzagi's cell experiment that when you apply sudden load on saturated soil, that load does not get immediately transferred to the soil. It get transferred to the water, and we have the development of this negative pore water pressure, which makes us feel that the soil is more stronger than it actually is. So we have to uh, do that correction also. So when your n is greater than 15 and dash is greater than 15, you have to assume that there is some kind of saturation soil is there. According to the code, you have to assume that there is some kind of saturated soil that this test or this sampler has encountered. So when do we do this correction? We do this for fine sand, silty sand that is saturated. Why? Because these sand can dilate under stress or maybe impact, and cause negative pore water pressure, thereby increasing the effective stress. So that is why we apply this dilatancy correction. No, I hope the most of what I said was recorded or you were able to hear it. Now, now I want you guys to answer this question. So according to this justification, whatever I have given here, what do you think should be the answer to this question? So, Bridge has already given the answer, but I want you to give ABC, because I don't know, maybe this is correct, exactly, very good. This C is the answer, saturated silt or fine sand, and yeah, both of you have given correct. And SPT value is greater than 50 after overload. Now next, on the last question for today is related to soil classification. So if you are preparing for GATE, I will suggest that I am going to read this question and going to solve this question. But I will be very happy if you can solve this question before me and give the answer to of this question to me. So I will read slowly. You want to mute me? You mute me if I will disturb you while calculating. But I want you guys to do this before me. within 2-3 minutes and tell the answer to this question to me. Sieve analysis on a dry soil sample of mass 1000 gram shows that 980 grams and 270 grams of soil passes through 4.75 mm and 0.075 mm sieve respectively. The liquid limit and plastic limit of the soil fraction passing through 425 micrometers sieve are 40% and 18% respectively. The soil may be classified as what? So let us draw the question. So when we perform sieve analysis, out of these 1000 grams, 980 pass the 4.75 mm. That means this soil is definitely not coarse because only 2% of the soil was retained above the 4.75. So it is definitely below sand or something. We'll see. And 270 grams pass through 0.75 mm. So the silt and clay ratio is also very less. It's only how much we say 27%, and coarse also is very less 2%. Only thing remaining is sand. So how much it is? 1000 minus 290. So we have more than 50%, right? 710. 71% of your soil is between 4.75 to 0.075. So it is definitely a sandy soil. So these options are gone. Right? Now let's say whether it is clayey sand, sandy clay, no sorry, clayey sand or silty sand. So for that we have to see, and they have nicely given us that they perform the liquid limit and plastic limit for the appropriate sample of the soil, and they got these particular values. So their plastic limit is 18% and their liquid limit is 40%. Now how do we go about calculating determining whether this is clay soil or silty soil? We are going to use the chart, right? You remember this chart? Remember this plasticity index and this liquid limit chart? A line. Can you guys tell me the equation for the A line? Yes, exactly. And when we put this point of liquid limit as 40% and the plasticity index is 40 minus how much? 18. So this 22%. What do we get? Is it above the clay line or below the clay line? So let us calculate 0.73 into 40 minus 20, 0.73 into 20, which is going to be around 14.6, which is definitely less than 22, right? So this value of the plasticity index that we calculate from this experiment is higher than the value of the plasticity index predicted by this particular line, right? So we have this soil above the A line. So when it is above the A line, which group it is? Which group soil is this? Exactly. So then it is going to be clay sand. Did you uh, did you also get this answer? Okay, very good. So yeah, that's all for today's session. Thank you for patiently staying along, and I hope you learned something. And tomorrow, yes, yes, yes. Tell me, tell me. Uh, oh, yes, 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 yes. You're right. You're right. That this range, yeah, this range, right? You are saying about this range. Are you talking about this range in the clay in this chart? Yes, 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 yes. That also 5 to 12. Exactly, exactly. 5 to 12%. Yes. But then no. So this I don't think they are going to complicate this much. But you are right. So if you had this dual option, then we might have to we might have had to check that. But also in that case, they will have to give us two things. First, they will have to make this silt clay uh, mixture as 5 to 12%, and also they will have to give us the liquid limit less than 20, right? They have to give us in this range. Then we can easily identify that we have to do dual kind of classification. Yeah, exactly. All right. So guys, we'll again meet tomorrow, 6 to 7. By the time I will be in IIT. So we'll have again three more questions related to our geotech, and so because we have to have 2 hour sessions, no sorry, two sessions uh, for this last 2 weeks, because gate exam I think for civil engineering is on 4th of the February, right? So we'll have tomorrow one session, and next Sunday and Monday again we'll have one session. Okay. Thanks, guys. Yes. Same 6 to 7. Okay. Bye. Have a nice day.